Welcome back everyone. In this lecture, we will continue with the representation theory of sl2c. In this lecture, we want to prove complete reducibility for finite dimensional representations of sl2c. So, let us begin with stating one important result. I am not actually going to prove. So, whatever ideas that we have seen so far, that will actually supply proof for this. So, you should take it as exercise. So, here is the exercise, which is actually a, let us say, proportion. So, what it says, let us start with the finite dimensional representation of sl2c. So, not necessarily irreducible. Okay. So, let V be an sl2 module. Okay. And suppose we have this W naught, which is in capital V, is the highest weight vector. Okay. So, of let us say weight m. So, we have V being finite dimensional sl2 module. Okay. And suppose that W naught in V is the highest weight vector of weight m. So, to begin with, this is going to be just a complex numbers. Okay. So, then what one can prove that m must be a non-negative integer. Okay. And this W naught generates capital V. Okay. And W naught generates, sorry, the submodule generated by W naught and the submodule generated by W naught, let us call it say W, has the following basis. So, the basis is given by this y power I W naught 1 divided by I factorial, where I ranges from 0 to m, and if you call this as Wi, okay, so then we have the following formulas, have the following basis satisfying the following formulas. Okay, if you take x Wi, then it gives m minus I plus 1 Wi minus 1. So, where we assume W minus 1 is 0, and then I varies from 0 to m, of course, and then h Wi is giving us m minus 2y Wi, and if you apply y Wi, that is going to give us I plus 1 Wi plus 1. Okay. And here again W m plus 1 assumed to be 0, where I ranges from 0 to m. Okay, we have already seen these formulas when we calculated things for SM. Okay, similar calculation actually tells you even for finite dimensional representation, finite dimensional irreducible representation V also we did the same calculation that corresponds to the highest weight vector m. So, very similar calculation actually tells you that these formulas are true, and on top of it one can actually prove that this submodule generated by this W naught is going to be irreducible. Okay. So, this has this basis, and not only that, one can actually observe that. Okay. So, maybe like I will leave it as exercise 2. So, if you combine these things, you get more information. So, given any 5-dimensional representation that has a highest weight vector W naught of weight m, so we have these conclusions. Okay. So, now what we are going to do, okay, we will take abstractly given m some 5-dimensional representation that looks like the span of Wi. Okay, let us start with m inside G plus, then consider V m, which is the span of Wi where I ranges from 0 to m. Okay, now we are considering abstract space spanned by some symbols Wi. Okay. So, this is some abstract space, spanned by Wi, and now define. Okay, let us call this a star. Okay, define the action of sl2c using the formulas that we have in star. So, then the claim is, then we can show that V of m is indeed sl2c module and it is irreducible. Okay, note that the dimension of V of m will be m plus 1. Okay, so note that the dimension of V of m is m plus 1. So, this is one way to actually construct 5-dimensional irreducible module associated with m abstractly. Okay. So, we take abstract basis Wi and then define the action using this formula. Then one can verify that these formulas actually gives you SL2 action on this V of m, and not only that, the same proof that we have seen in SM actually tells you that this must be irreducible, because the action of x actually brings down the indices. So, it goes from I to I minus 1, and the action of y actually increases the indices from I to I plus 1, and h actually makes it stable. So, using these actions one can immediately show that the abstract module that is defined using these formulas going to be irreducible. Okay. And we also seen explicitly how one can construct using this homogeneous polynomials of degree m in 2 variables. Okay. So, very similar to that. So, now using this you can actually see that this module that we have here generated by this W naught almost looks like irreducible module corresponding to this highest weight m. So, indeed one can prove that this W will be isomorphic to V of m, because all these vectors are non-zero. So, that means they are basis for this W, and W will be isomorphic to V of m. So, that also I will leave it as exercise that immediately follows from this proportion. So, now let us make one important observation. If we start with the finite dimensional representation, let us say finite dimensional representation of SL2C, then we can always have highest weight vector. Okay. We can always have a highest weight vector inside capital V. So, how can one can guarantee this? So, let us look at the operator H that is acting on capital V. then because H is acting on a finite dimensional space, it must have an eigenvalue. Let us take vector W to be eigenvalue of eigenvector of H with eigenvalue A. So, that means H W should be equal to A W. Now, use this action of x and then see that x W is going to lie inside V A plus 2. So, now since all these A plus 2 k's are all distinct, so that tells you that there exists some smallest k for which x power k plus 1 W is actually not 0, and then x power k W will be 0. Okay. Now, what one can do, one can replace V by x power k W as before that we have seen in the analysis of finite dimensional irreducible representation. So, then we have H V equal to some lambda V, where lambda is exactly A minus A plus 2 k, and then x V becomes 0. Okay. So, this tells us that there is always highest weight vector inside capital V. So, of some weight lambda, okay, highest weight lambda. So, that means using our earlier analysis, we can observe that this lambda must be in Z plus, and this submodule generated by this V inside capital V, this is going to be isomorphic to V of lambda. Okay. So, in particularly we have this embedding of V of lambda inside capital V for any finite dimensional representation of capital V. So, this is something very simple. Okay. Actually, one can prove this in many multiple ways. For example, we can look at all possible sl2 submodules inside capital V. Okay. So, basically consider the set V dash, where V dash is sl2 submodule. Now, we can actually put inclusion as partial order in this. Okay. Now, look at the dimension of all these spaces. Okay. If I take V dash which has smallest dimension, let us assume V dash are all non-zero. Okay. 0 space we do not need to worry about it. So, you consider all possible non-zero sl2 submodules, then we can actually take a dimension of all of them, then there will be a minimal dimension achieved. Okay. So, there exists V dash here in this set, in this collection, such that the dimension V dash is minimum. So, now V dash must be irreducible, because if it is not irreducible, then it will have proper non-zero submodule. Okay. That will actually give you smaller dimension module. So, that we cannot have, because this is the minimum dimension that we have. Okay. So, more or less this general argument forces that any given finite dimensional representation, there is always irreducible sub representation. Okay. Now, given that any finite dimensional irreducible representation is isomorphic to V of m for some m inside Z plus. So, we can actually have this same statement using this general discussion as well. Okay. So, these observations actually will help us to actually understand more about representations of sl2. So, now we will actually move on to understanding general representations. Okay. So, here is the important thing. Okay. So, if you have some operator, okay, so what is we are really trying to do? We are actually trying to prove complete reducibility, okay, completely reducible property. So, if you are actually aiming to prove something is completely reducible, that means it is direct sum of irreducible representations. Okay, then we should actually propose some way of decomposing given module, some algorithm to decompose. Okay, how one can achieve something like that. Okay, it is some general nonsense. So, let us start with some operator. Let us call it operator let us say T. So, this is let us say there inside endomorphism of V. So, let us say V is given finite dimensional representation of sl2c. Okay, and this idea works for any representation. Okay, I am just demonstrating it for finite dimensional representation of sl2c. So now choose this operator T inside endomorphism of V such that T commutes with the action of sl2c. Okay. So basically you are looking at all possible. So sl2c to this GL of V, which is endomorphism of V. Okay. So you have a map phi. So phi is the representation, this is the representation. So we have this phi of x, phi of h and phi of y, all of them are elements inside this endomorphism of V. So now what I want T such that it actually commutes with all of them and so on. Okay. So once you have such representation, such operator, then what I can do with that, that is the question. So one can actually immediately talk about primary decomposition of this V with respect to T. So one can talk about generalized eigenspaces and one can write V as direct sum of generalized eigenspaces. Okay. So let us recall, for given theta in C, we can define what is called this V theta. So let me put it theta here on the top. So this is, I want it to be generalized eigenspace, generalized eigenspace corresponding to theta. So what it is, this is those vector in capital V such that when I take T minus theta identity on V, some power of that should kill this vector V. Okay, for some k in z plus. Okay. So note that from general theory of linear algebra or linear operators, you know that okay, there is actually some unique number for which this all will be killed. Okay, on this V theta at least, because so this T minus theta identity, that is going to be nilpotent operator when you restrict it on V theta. So obviously T minus theta identity power dimension of V theta will be 0. Okay, that is what the general theory says, but anyway this is good enough for our definition. So now what one can have, V can be written as direct sum of V theta for various theta. Obviously V theta could be 0, whenever V theta is non-zero, that will be called generalized eigenspace. Anyway 0 space and all we do not care. So let us say that only for finitely many thetas this V theta will be 0. V theta will be non-zero for only finitely many values of theta. Because the V is finite dimensional. Now what is special about this V theta? Okay, it is a simple exercise. If phi x commutes with T, then this generalized eigenspace will be invariant under phi x. Okay, so it is a simple exercise, because if I take T minus theta identity V power k, V is 0. So this is capital V. So then if I take x V and then look at T minus again theta identity applied on k. So since x t is equal to T x, you can see that x can be taken out and then this will become T minus identity power k V, which is 0. So this tells you that x V is again inside V theta. So if you have operators, okay, that commutes with T, then the generalized eigenspaces of that operator will become invariant under that operators. So in particularly it will be invariant under all these operators, phi of x, phi of y, phi of h. So in particular it will be invariant under entire sl2 action. So that means V theta becomes SL2 submodule. So, V theta is a SL2 submodule of capital V. Okay. So, we have this V being direct sum of V theta, theta varies over C. This is indeed SL2 representation decomposition. So, decomposition of SL2 representations. Okay. So, already we have proposed one method to actually decompose V into direct sum of some smaller representation. Of course, if you take another element from endomorphism of V, which actually again commutes with all the operators of SL2, then you can have another decomposition. But if you want to actually somewhat interconnect between theta and this new, let us say, theta dash, so then you demand that theta and theta dash again commutes. Okay. If you have another operator theta dash such that theta dash commutes and theta commute with any g comes from SL to C. So, then you can see that this theta dash actually leaves this V theta invariant. So, then you can decompose V theta into further as generalized eigenspaces for theta dash. Then you can actually have further decomposition of V theta into SL2 representation. So, this way we can keep actually kind of getting decomposition of SL2 modules. And of course, it has to stop at some point because you can't keep on decomposing further and further, you can reach max irreducible. So, for that purpose we need to have lots of elements that commutes with the action of SL2s. Okay. So, we will see that in the theory of semi-simple Lie algebra. So, we talk about what is called the center of the universal enveloping algebra. So, that is indeed really huge. It is going to be isomorphic to some polynomial algebra. So, it is indeed very big algebra inside sitting universal enveloping algebra. So, if you take images of those elements inside your endomorphism of V, then they all will commute with the action of G. So, that way you will be getting rich number of elements that will be actually helping us to decompose our representation into smaller representation. But indeed we do not need really the full power of all those elements that comes from the center of the universal enveloping algebra. All we need is just one element, which is called the Casimir element. Okay. I will actually give the definition of the Casimir element for SL2C now. So, later we will see how to define that for general SL and C and so on. So, since I have not actually defined what is the universal enveloping algebra, so we will just define it in the endomorphism of V itself. So, it now looks like depending upon the representation that you choose, but one can actually make sense of some universal element that actually comes from actually the universal enveloping algebra. Okay. So, what is Casimir element? Casimir element of SL2C. So, note that V is, let us say, finite dimensional representation of SL2C. So, let us call this phi, which is the map from SL2C to GL of V. Again, I am identifying the action, everything in terms of this. Okay. So, now I am going to define this C from V to V, where C is given to be phi of x, phi of y plus phi of y, phi of x plus of times phi of h square. Okay. So, this is the map that we are interested in. So, there is actually very good meaning in terms of there is something called killing form. So, basically we are looking at the basis and its dual basis, the basis being x h y and its dual basis, again one can compute, that is also going to be this y, sorry, if x y h, then it will be y x h again. So, this thing can be written in terms of that. So, it has some deep meaning, it is not that some random element is written here. Okay. So, but now for time being we can take this as definition. So, now this is an element inside endomorphism of V. Okay. So, I will leave it to you to check this C commutes with SL2 action. Okay, I will stop here. We will actually continue with complete reducibility of finite dimensional representations of SL2C in the next class. Thank you.